saying like if I have to leave.
I'm pretty sure that
You're just supposed to plug it in to a calculator.
Yeah, I know.
Airway.
That's what I did.
I'm
pretty sure
airway.
when
Say airway. Debe ser.
Do it in Desmos and makes life easy. He saves
That's what you like.
Actually, yeah. Just
Ocho días era una general de tubas muy importante. Y ganó muchos batallas. Y ayuda.
Hey friends,
Ayudaba a.
once you get in here, we got a little pair deck action.
Oh.
I'm totally.
wow.
So I have
took me like 2 seconds to do that.
2 tabs open of the chemistry textbook. And I have this open and then
All the chemistry.
rolling over.
Away.
Yeah. Okay, I'll highlight.
All right.
Get rid of that.
Go ahead and join us on the pair deck if you would. A couple of things here. It's Monday.
Make sure you're in radio.
You don't need to worry about getting your analysis submitted. You already did that, right? So we'll get that into the gradebook at some point. Your tests that you got back on Friday, those are in the gradebook, so you know where you're at. The first try final. The first try final is Thursday this week. It's CBPM and CAPM stuff. Okay, it's 20 question, multiple choice. But I'm double weighting it when it hits the gradebook. AP exams. We can't complete the something until you pay for it, and there are quite a few that still need to pay for it. If the payment, I don't know, if it's not taken care of soon, they'll come after you with the baseball bats or something like that. But yeah, sort that out. I'll put the link up here in a little bit. But that's other stuff going on. I think that deadline is today. So if you want to, I'll post the link a little bit later in the period. Send that to the appropriate people or take care of it yourself. But we're going to have that sorted out. Practice determining FU in an elevator. That's what we're doing today. So we have this expression that you determine as a result of the lab that says that acceleration is equal to FU divided by mass, okay? We got some other things that we know about acceleration as well, and so our goal here over the next little bit is to learn how to merge our understandings of acceleration together. That's really kind of the key to doing well in this unit of study. I don't think we're going to have an exam over this stuff before the end of the trimester, but again, we might have like a mini one here in a couple weeks. We'll see. That wouldn't be a couple weeks, it'd be the 13th. A week from Tuesday. How much are we really going to get in? I don't know. Anyways, you're here with this pair deck, and this pair deck goes along with a video that I've got for you here on what's called a laser disc, kids. Behold the future in 1987. All right.
That remote is huge.
You should see the disc that goes with this remote. I'll show you
What
later.
happens to your weight in an elevator?
Okay. I don't know if you've noticed this down in the 9th grade wing where they've got all the marble on the walls. There's actually a bathroom scale in the elevator.
What does the 157 pounds mean? Why are we getting a reading of 200 pounds on the scale? The elevator is still moving. What must be true of the speed, since the scale reading has returned to 157 pounds? What is happening to the elevator now?
Guy asks a lot of questions, right? Okay. So different phases of the motion. There are different readings on the bathroom scale here. But when the guy steps in and he's standing on the scale, it reads 157 pounds. If you're not familiar with pounds, that's what Americans use when they mean to say newtons. Okay, we won't worry about the conversion necessarily right now, but you can represent force with pounds. Okay, so kind of 5 phases of the motion, and initially, it's so topical. We can hear an elevator operating in the background. Okay, that's the elevator. Yep, it's hydraulic. It's not somebody going to the bathroom. That'd be kind of scary. Okay, 157 pounds. That's the reading initially on the scale. That's when the person steps in. So if I back this up, oops, aiming at the wrong thing here.
What happens to your weight in an elevator?
Boop.
What does the 157 pounds mean?
Okay, so right there, the door is closing, and if you look at the scale reading, it's 157 pounds. So, boop, what just happened there? That's not what I wanted. That's what I wanted. All right, so draw an FBD and an FAD, which is to say a HBD, a force addition diagram. When the scale reads 157 pounds and the elevator velocity is 0. The dot there, that's the guy. So if you want to kind of anchor your free body diagram to that, and then just think about what the force addition diagram would look like, the happy birthday diagram. If you perceive any arrows to be of the same length, just throw tick marks on them. What's up, boss? What's the code? Great question. I'll throw that up here.
ILEKH.
Anybody got the join code for code there?
Yeah, we keep the second or 3 of us. Potential.
Ooh. Oh. Here, we'll do the 2-screen experience.
I'm not ready for this.
KH.
Yeah.
ILEKH.
And maybe.
Yeah, well.
There you go. So if you're not in, ILEKH.
Thank you.
This cannot stand. We're going to choose an ugly green color. That one. Yes. And then just move it in position.
Obviously.
Get the right side. There we go. Look at it.
All right, let's see what we got back here. So I'm going to project a pear deck in the back. So if you take a look at what folks are throwing on there, looks pretty consistent throughout. Okay, 157 pounds up, 157 pounds down. As far as feeler dealer, is anybody going there? Thoughts on this? Oh, it's not scrolling. I got to go back there to scroll. That's sad.
So much.
All right. What feedback would you have for this person on their feeler dealer? Okay, so what do they need to understand here? Okay, there's not a considerable enough interaction gravitationally between the elevator. Yeah, so what is going to deal a downward force on our guy here? Earth gravitation. Okay. Man scale, man earth. Nice color choices. Man scale, man earth. 157 pounds, 157 pounds. And if you see TDM, it looks like that, right? We've been there, we've done that. That's BFPM. Nobody's mind is blown there too much. All right. But then in the next little segment here, maybe aim at the right thing. Hits the button.
Why are we getting a reading?
Ooh. Whoa. Look at that. Okay. Now, in the old timey days, speedometers and scales, right? If it goes above this, now we're into the 200s. Okay. So it's not reading 12 pounds, it's reading 212 pounds.
I think that's
Okay. So there you go. When the scale reading shoots up to 212 pounds, now the velocity of this elevator is no longer zero. Okay. What is the free body diagram going to look like here? So go ahead and have it that on the dot.
No longer equal. This one's a whole lot.
So the scale is reading 212 pounds. One of the things that I don't have in this pair deck that I kind of wish I did would be a spot for you to think about what the velocity versus time graph looks like. We did this in the last unit, right? Wasn't there a problem with an elevator in the mastering?
Yeah.
Okay. Kind of think back to what that velocity versus time graph looks like. Ooh. That's what I'll add in at lunch. I'll have you draw the velocity versus time graph. By you, I think. 5th hour. So the scale reading's 212 pounds.
Oh, but still that of the yellow color. It's the normal size and not that of the yellow.
Let's see if I can show 3 things at once. Yeah, that's real easy to see, yeah?
Oh, yeah, you know it.
Yeah, huh?
Oh, yeah, you can control
Boo to
that.
that. How about if I go this way? Oof, okay. So here's one person's story.
Yes.
You got a 212 pound smoosh poosh and 157 pound gravitational force. Or, oop, things are changing. I didn't lock it there. Or 212 pound smoosh poosh, 157 pound gravity. They're in the process here. I should have waited a second, but another 55 pound downward force. So I think kind of contrast what the forces are saying here about this person with what the forces are saying here about this person. The initial velocity was 0. At this point in the motion, the velocity is no longer 0. What has to be true of the forces? What has to be true of the motion? What has to be true of the forces? So kind of ponder that with regard to what you're drawing there for your diagram. And if I go back to let me go back to the video. You don't have like a velocity time graph or a motion map or anything. Really, you're gauging the motion based on this open door in this scary 1950s elevator that this person is riding in here. So let me back it up.
7 pounds medium.
Okay. And watch the elevator door in the background. It's not moving. Now we're moving.
The elevator is still moving.
Okay.
What must be true?
So in between, when the guy steps into the elevator, the scale reads 157 pounds. And again, keep in mind here, that was when the velocity was 0. Now there's a moment where it reads 212 pounds. The velocity very clearly is not 0. Okay? We've returned, though. The elevator was still moving by in the background, but the scale is more or less reading 157 at this point in time. But the velocity is not 0. So if you're thinking about a velocity versus time graph, and maybe we need to do, I can't not have this draw it, man. Sorry. Not a text answer, but a drawn a grid. Let's try that. Is there a grid?
Sure is a grid.
Hey, cool.
Problem is we're set.
So here's what I'm looking for you to do on this grid, friends. And you can kind of ignore how that grid is set up or whatever, but on this grid, can you draw a velocity versus time graph? Now, hey, here's the thing, friends. There are kind of 5 phases of motion. Phase 1 is when the scale reading is 157 pounds, velocity is 0. Phase 2, we're going to pretend that that 212 exists for a period of time. Okay? So join me here. That 212, we're just going to pretend that that's a constant reading for a bit. Then the scale reading goes back to 157, but the velocity is not 0. We see the door moving by in the background. And then phase 4, it drops down to 120 pounds. We're going to pretend that that's over for a period of time. The scale reading is 120 pounds, but the velocity is non-zero. And then at the very end, the scale reading goes back to 157 pounds, and the door opens because the velocity is 0. So could you do yourself a little favor and think back to what the velocity versus time graph must look like for that?
Should we draw in where we think?
You're good, I think, if this is you. Is this you?
I don't know. I switched the colors after every line.
Whoa, yeah, you did. Whoa. What are you drawing with, Riley? Your finger? Cripes. Are you on a school bus right now?
I can kick your chair up.
Is that what's happening? Jared, knock it off. Poor Riley. It's okay, Riley. All of us have different things that we're really good at. Are you cold? Maybe that's what it is.
That's what you're using?
You're fine. Aight. Okay, so everybody's kind of smelling the same thing here. If we take a picture, take a gander at the different velocity versus time graphs, it kind of looks like a, would you say a fedora? Okay. I better lock this before somebody draws a pair or something. I'll give it back to you. I'll give it back to you in a second. But we've got kind of a reasonable consensus, horizontal, and then you've got a positive upsloping line. Then you've got horizontal, non-zero. Then you've got a downsloping line. Some people, I think, are already supposing differences between the two sections that have acceleration. So that's kind of cool. And then it ends with another horizontal section. So I think pretty much universally, your understanding of what the velocity versus time graph will look like. And that's good. So let's go back then to this 212 pounds. If it's accelerating, what must be true of the free body diagram?
It's unbalanced.
Unbalanced. It can't be balanced. Okay? So be mindful of that with your diagram. If you're saying that the HBD would show balance, that disagrees with what we're understanding here, that on the velocity versus time graph, we've got an upsloping section like that. Okay? 2, let's talk about directionality here a little bit, because this is gonna be a thing that we've got to think about with regard to the free body diagram. This is positive acceleration, and as our friend Ethan would say, this would be the negative acceleration here in that part of the graph. So we've talked about representing velocity as an arrow. We can also represent the acceleration as an arrow. And I think that's an important thing to think about in your free body diagram, that during this portion, the acceleration is in the direction of motion, and that's why we're getting faster. Okay? So your acceleration would point up there. I could write that here, right? So we think acceleration is pointing up. During this section, the acceleration is negative. but the velocity is non-zero and positive. It's still moving in an upward direction. It still has a positive velocity, but the acceleration is pointing in the direction opposite the velocity. That's why it's slowing down. So please be thinking about that. I'm looking at your HBDs here. Could you add the FU to your HBD? Okay, so you've got a line weight tool there. You can use that to make a fatter arrow and maybe make it in a different color. What are you thinking the FU arrow looks like for your HBD there?
I can't. That was a mistake. Oh wait, we can do it in highlighter. That's a good idea. We'll do it in white highlighter. Really big. You can't see half of the arrow. That is fine. It's beautiful.
I don't want to spoiler this too, or I do want to spoiler this. If you've noticed, like, wow, Mr. Harding seems to be swearing a lot less than normal. What I'm doing over here on the computer while we're pair decking is I've got it running in screencast mode, so I'm going to record this. So then for Ethan, when he gets back, Ethan, you are here. I thought you were. Don't you usually sit there? Yeah, that threw me off, man. I counted you absent. Don't do that. Sit in your spot. Jeepers. That's why we have a seating chart here. Oh wait, we don't. Anyways, so I'm screencasting this and I'll post that for you later, right? Like notes and stuff. Is that helpful? I don't know. I'll find out when I survey you later. Okay. Oh, Mr. Connor does it too. Great. Oh, now I'm just on his coattails. Mr. Connor, the teacher that leads. All right. I suppose you think if Mr. Connor didn't shave for all of November, I wouldn't shave either. Fair enough. All right. So let's take a look at what folks are throwing in here. So if you look in the back, I'm going to lock it quick. And some of these FUs are pointing up, and some of these FUs are pointing down. So can you take a moment to chat with your neighbor about the direction of the FU here? What should the FU be telling you about the forces that are acting on the person? The forces don't balance. Remember, the forces don't balance here. The forces are unbalanced. The goal of the FU is to show you how unbalanced they are. I think you could probably put a number value to that FU as well, right? You could do math. This is West High.
Math is hard though.
How unbalanced are those forces?
Not equal. No, wait, yeah. It's a struggle game. Oh, I didn't even do that.
All right, so let me switch it over to this quick. Le boop. There we go. And I think I can do boop. Okay, so I've got this thing. Most people are showing 157 pounds down, 212 pounds up. So in comparison, I've got an excess of force pointing up. How much more? 55. Okay. So if I put those together in an HBD, I've got 212 up, 157 down. If I wanted to balance them, I would need 55 additional pounds in the downward direction. I don't have that though. So that's not what we're trying to do here. We're not trying to balance this. We're trying to say how unbalanced it is. And so that's going to be represented by an arrow that looks like this. This is my FU, and it's 55 pounds. Okay? FU arrows don't follow your rules. Okay, the name kind of implies that, right? It's not going to do what you want it to do. FU. So it's going to put its butt on another arrow's butt. It's going to put its head on another arrow's head. Okay, that's what's happening there. It's not a force. It's the unbalanced force. And in this case, that's 55 pounds. And it's in the upward direction. All right. So something else to be mindful of, and this is what I'm asking you to think about including, in addition to the FU arrow, I think it's helpful, maybe even before you've drawn it, to be mindful of the direction of the acceleration. This is not a force, so I'm not putting it in the free body diagram or attaching it to this thing. I'm just to the side for reference, demonstrating the direction of the acceleration. I'm aware that this thing is accelerating upwards. That's why it's getting faster in the upward direction. Okay? So let's switch back over to this thing. Oop. And
of the speed.
okay, so now we've got the scale reading kind of bouncing around. You can see the door moving in the background, but the scale reading is kind of bouncing around at about 157 pounds. So let's get on to this one. What is this diagram going to look like now? The scale reads 157 pounds. Back to reading 157. The velocity is not 0. So this is section 3.
I really need to check this. We're gonna go with not white. Ooh. That's nice. Why? Sorry. We need to do
Again, like,
arrows do you want?
what are you asking me?
Do you want just the FBD and the FAD?
If you want to just, sketch the HPD off to the side. You don't need to type a whole lot of stuff here if you don't want to. Or draw frogs if you don't want to. I don't know. I know who you are, so be mindful of that.
You can't see everyone in today.
I can. Yeah. You
So
can.
know who's drawing wrong.
Yeah.
That's okay.
Which frog are you drawing, I guess, is the concern. All right. So how are we looking here? All right. Looks like we're on board. So what's true of the velocity at this point in the ride if the scale reading's back to 157? Constant velocity. What has to be true of the forces? They got to be balanced. Okay, so that's what's going on here in part 3. So we saw a horizontal section on the velocity versus time graph. All right, cool. So moving on. Now all of a sudden,
157.
whoa,
What is happening?
whoa. Okay. You've ridden in elevators before. Chances are, if not, we can send you out here for a little field trip.
Let's do it.
Although really, amongst elevators around town, this one's kind of boring. But you have these sensations. If we're taking an upward trip in the elevator, you hit the button, it starts heading up. Whoa, you feel a little heavier. Okay, it gets to the top. Whoa, you feel a little bit lighter. That sensation is all based on how hard the floor is pushing up on you. Your perception of your weight isn't necessarily based on your gravitational interaction with the Earth. It's based on the smoosh poosh you're experiencing from beneath you. So that, you can think of different situations that operate like this. In an elevator, you get these apparent changes in weight that you can perceive. But other times too, in cars that go vroom, okay, or on a roller coaster, your perception of your weight is actually based on the smoosh poosh interaction. Okay, so here we are. The scale reading is I guess not 120 but 122. 122, that's boring. Do it for 120 or don't. But what is this going to look like? Some things to consider. During this portion of the motion, think about what that velocity versus time graph looks like. What must be true of the direction of the motion, aka the velocity, and the direction of the acceleration if this thing is slowing down, okay? So you might also consider adding in that arrow off to the side to orient yourself with respect to the direction of the acceleration. And then note how that compares to the result of your free body diagram and your HBD here. Velocity is not constant during this phase of the motion. Forces must not be balanced. How unbalanced are they? Well, again, this is West High. You're good at math. But in addition to the magnitude of it, you've got to be mindful of the direction of it. Can I ask you a favor? FU is not a force, okay? So please don't include it in your free body diagram. You can include it in your force addition or your HBD diagram, but it doesn't have a feeler dealer. So let's not draw that on the free body diagram because it's kind of confusing to me as I'm scrolling through some of these, seeing what you have going on there. And again, this is where I'm seeing some issues with the direction of it is if you're trying to include it on your free body diagram. So that's my recommendation, that you not draw the FU in the free body diagram, but rather reserve that for the HBD. And again, if you take a look in the back, you can see, looks like most folks have that FU pointing down. How does the direction of that FU compare to the acceleration here? Same. How did it compare in section 2? Acceleration was up, FU was up. And now we have acceleration down, we have FU pointing down in most cases, okay? So if we look at this example here, you've got 122 pounds up, that smoosh poosh man comma elevator. The elevator's not pushing up on you as hard. When you get to the top, right, that's the fun time to jump in the elevator because you get like that extra inch or two of vertical. You wouldn't jump in elevators though. You're not those kinds of kids. And the 157 pounds downward, why are we still drawing 157 pounds down?
Gravitational constant.
Yeah, not changing his weight, okay? His mass is unchanged. His gravitational interaction is unchanged. All right. Moving on to the last one here. And again, you can streamline this. Don't worry so much about feeler dealer here. I hate to have you typing the same stuff over and over again. But we're at the fifth portion of the ride here, as it were. What are we going to see in terms of free body diagrams here?
That's not right.
Wow. Please don't. Whoa. Yeah, I was going to say. All right. So we're looking at that in the back. Return to a constant velocity of 0. Forces are balancing. Okay. Sections of this, sections 1, 3, and 5, I'll give it back. I'll let you have it. There you go. You can finish that out. I'll hide them. Sections 1, 3, and 5, then, these are BFPM. We've dealt with these. CVPM, BFPM. Okay? And so that's 1, 3, and 5. So if we were doing this like a practice the model problem, those are the CVPM sections. 2 and 4, though, we're going to treat them like they're CAPM. And so that would be unbalanced force particle model. Okay? So here again, CAPM, unbalanced force particle model. So these next couple of slides then are dealing with that. So here's a little bit of information for you. It turns out that a Newton, in terms of force, is roughly a quarter pound. Okay? So if you were going to go over to England and go into McDonald's and order a quarter pounder with cheese, they don't call it a quarter pounder. They call it a Newton with cheese. Okay? So get your cheese Newton, and it tastes just the same, other than the mad cow part of it, but that comes later. But that's about how that shakes out. Or an apple. Okay, an apple, that's roughly a Newton in terms of force. That's about a quarter pound there. Different ways of trying to understand it. So conversions-wise, I know you like 4 sig figs, so that's why I'm telling you 4.448 newtons is equivalent to a pound. Also, a kilogram, if we put a kilogram on a bathroom scale, it's going to weigh about 2.2 pounds. So what I'm asking you to do on this slide is to determine the acceleration of the elevator when the scale reading is 212 pounds. Okay, how are we going to do that? Well, you got to think about a couple of things here. Can you use the information we have to figure out the mass of the guy? Well, he's 157 pounds. So what's that going to shake out to in kilograms? And then you can use your, I don't know why I rewrote that again. You can use your diagrams to think about what the FU is in pounds, and then again, 4.448 newtons per pound. So go ahead and slap that out with your neighbor or yourself and see what you end up with for an acceleration for the elevator during that part of the ride. What is the acceleration of the elevator when the scale reads 212 pounds?
212.
Yeah.
Are these kilograms there? Or are you using Okay.
Okay, so this is
Are you typing that?
Why wouldn't you?
Open a new tab and calculate.
Oh no, Riley. No. Please no. Anything but that.
Riley, what are you doing?
I think what are you doing? It was not my idea. I am not responsible for this. I'm gonna do this and hope that does what Mike said. It probably won't, but it might. Hey. Cool. Is that nope? I lost the breath. I lost the. Oh, that's not right.
Oh,
Yeah. Divide is actually. Oh, you need to say divide the instead of the.
ooh, is there a? Did I make a mistake here? What do we got here?
Riley, what do you?
Okay, I forgot to put in this.
All right, so friends, when I'm looking at this here, you don't have to play the mistake game in Pear Deck. A kilogram of mass weighs 2.2 pounds. So when you're talking about the mass of this guy, if he's 157 pounds, his mass in kilograms should be a bigger number or a smaller number than 157.
Smaller.
Right? That's a smaller number. So be mindful of that. Okay, 2.2 pounds for every kilogram. So check with your neighbor on what you're using for the mass of this fella.
For the 212.
He's a 157 pound guy.
Oh, that's.
Is his mass changing when it's 212 pounds? No. So you don't need to convert everything into kilograms. You just need to say, when he's at rest, he's 157 pounds. What is that in kilograms? That's his mass. And that's going to be his mass at all points in the motion. You're using these other scale readings then to establish what the FU is in pounds. And once you know it in pounds, then you take that into newtons, and you can kind of sort this out. That looks a little better.
Doesn't matter. I just copied over the entire thing. So we have this.
So other stuff I'm looking at here, and again, mistakes aren't mandatory in Pear Deck. What you're dividing by here, this should be the FU. How big is the FU when the scale reads 212? About 55 pounds. Okay. That's what you're going to want to convert from newtons into, from pounds into newtons. 55 pounds. So how big of an FU is that? And again, if you read the top of the screen, there are 4.448 newtons per pound. So if the FU is 55 pounds, what should be true of the FU in newtons then? A bigger number or a smaller number? Bigger number. Okay, so be mindful of that. So check your math there a little bit before you get on some kind of long text typing screed. Maybe double check and make sure that you're establishing the correct value for the FU. The FU.
That's backwards.
Right. Interesting number. See, my equation is right.
You know what, Riley?
I have to rewrite my whole.
Neither do I. I only have to rewrite one thing.
Lovely.
Okay. Times that one word right there needs to be replaced.
All right, let me hold this for a second. So I want to show you the kind of the two different threads that I'm getting here. I'm seeing 0.708 meters per second squared, and I'm seeing 3.42 meters per second hopefully squared. Maybe I stopped them before they finished typing. Those are the two different answers I'm getting, and I think some of you have had either or both of those at some point. So could you please chat with your neighbor a little bit, how you're establishing what the FU is, how you're establishing what the mass is, how you're establishing what the acceleration is.
Maybe it doesn't like the division, because that is a possibility.
Wait, you wouldn't multiply it. Why are you multiplying what's already at?
Yeah, you is 55 times.
So the fastest elevator over Shanghai Tower is 20.5 meters a second.
Wait,
So it's
45 miles an hour. Do they evacuate? Is it like pressure? Reduce the pressure in the channel?
Like, my question is, how fast does that elevator accelerate?
Yeah, exactly. That's what I want to know.
That's a lot of newtons.
Yeah, it is.
Oh yeah. This is 55.
That's how much
Number the correct way, right?
All right, so let's take a look at this here. And you can kind of coach me through it maybe a little bit. So the free body diagram here, you're going to have 157 pounds down. You've got 212 pounds up. So if I put those together, I'm going to end up with an FU pointing upward. It's 55 pounds. Okay. So one of the things I've got to do is take this FU from pounds into newtons. It's 55 pounds, and there are 4.448 newtons for every pound. So what are you getting for that FU? 200 something? 245 newtons. Okay, so that's the FU in newtons. And then his mass. So it's 157 pounds. But then think back to kilograms and pounds. So we've got 1 kilogram for every 2.2 pounds. And so that's going to shake out to something in the 70s. What do you get there? 71 kilograms. Okay, so then if I want acceleration, that's the FU divided by the mass. So I'm just going to take the 245 newtons divided by 71 kilograms, and mental math, this is somewhere in the ballpark of 3.2, 3.4. And we do dimensional analysis here, and we get newtons per kilogram. Wait, what? It's supposed to be an acceleration. Keep in mind, we looked at this the other day in the lab. The newton is equivalent to kilograms times meters over second squared. So effectively here, when I've got newtons divided by kilograms, I'm taking kilogram meters per second squared, and I'm dividing that by kilograms. Kilograms cancels out, and this is equivalent to 3.4 meters per second squared. So dimensionally, that shakes out to be an acceleration. Okay? So somewhere in the ballpark of 3.4. And then the last one here, what is going to be the acceleration when the scale reads 122 pounds? Nothing has changed about his mass. He's still 71-ish kilograms. But the scale reads 122. So think about what that does to the FU. And can you sort that out into an acceleration? Dear Riley's.
I'm concerned about the influence that Jared is having on Riley.
The director's already gonna write it out.
Hey, totally cool. It looks like a lot of you are being very aware of the direction of this acceleration. Okay? If conventionally we say that vertically upward motion is positive, then the acceleration here is somewhere in the negative ballpark. And I was, of course, very helpful and just left this on project answer mode for you. So, well, according to what everybody else is typing on the front screen, Mr. Harding, it looks like it's about negative 2.2 meters per second squared. All right. But yeah, that's the idea. So 122 pounds minus 157 pounds. Take that times 4.448 and then divide that by the mass in kilograms. And there you have it. All right. So that's the size of it. So that's kind of the gist of it. You're going to take the free body diagram, put that in a HBD to figure out what the FU is, what direction it is. Hey, and a really important consideration here, think about the direction of the acceleration because that's going to help you identify the direction of the FU. Here we saw when the FU was up, acceleration is up. When the FU is down, the acceleration is down. All right? That's it.
That's most time. Spanish, Andre.
P4 elevator. Yes.